I've done this 3 times now in public, so anyway. I would like to spend the time, if I get any time left once this thing has booted up, to talk about how to look at how to interconnect boxes inside a network. With boxes, I mean the routers and the other elements that, I can hear myself. The routers and the elements in there that we used to, can somebody turn the volume down a little bit? Yeah, but okay. It's about to be a loop, packet loop. There's no CTL on this. So there's a lot of things that you can and can't do, and there's other possibilities today of interconnecting things inside the network. Okay, and I'm trying to look at the thing and say, what can we do and what can't we do? And there's also another. I would like somebody to turn the volume down a little bit, but anyway, there's also a problem here with scaling. How big can I build a network? How do I do in order to add more stuff? And as an operator trying to deliver decent services, we are limited by the stuff that we can buy that actually works. I mean, there's a lot of stuff you can buy. There are empty shelves that doesn't really deliver packets, and the things you can buy are not really the rocket science you want. Now it does a very funny thing. It says 90 something, and then it jumps backwards, just to make me much more worried about it. How much time do I have left? So far we've been watching, we lost 10 minutes on Bill, okay? I really would like to have the slides, otherwise this perfect my image again. Working and protect. You have to do like an ADM. You pick the working part bits coming. Look, we're not there yet. Okay? This is ATM to the desktop technology. This is how to make it work. The thing with the antenna on the back is the wireless device. This all started when I wanted to, let me tell you what I tried to do before. My computer was working just fine and I plugged into the network. And everybody knows that if you plug into a network with this thing, so you have to reboot it. And I wanted to get the picture that I took in Jerusalem, which is the grave of the engineers. Because one of my topologies looks like some kind of religious stuff. And the story was that when some of the Roman kings, or whatever they were, wanted to rebuild the wall around Jerusalem, the engineers that built it forgot one of the buildings that was important. It was the building where King David was buried. So they chopped the head off of the engineers. There's the grave of the engineers. So I wanted to show that to see what happens if you do this wrong. Now, I run into this, the Liberation for Work, the Working Internet Liberation Force, they came to us and said they will blow up our building if we don't do certain things. And they wanted an internet that can move any kind of packet. They didn't want me to optimize the network for just World Wide Web or something else. They didn't want me to build something into the middle of the network that was a limitation. They were perfectly happy to the limitation. So I asked them, what limitation would you accept? I mean, and they said, well, the amount of green money we can give you. So I said, that's fine. That translates to, if you're doing limitations in the network, they have to be at the edge. It's sometimes useful to send packets. The Ethernet has given us a wonderful tool that I think the airlines now have adopted. If you go to the security check and you try to put your carry-on luggage in, you can't get it in because they have the screening thing, the metal thing, and you have to try really hard to get the two big suitcase in. And this is 1,500 bytes delivered by the Ethernet people. But inside the network, you really want to do something better. The Internet Liberation Force also want enough buffering, and there is a problem here when the network gets very, very, very big, very, very big, and TCP may not work the way it's supposed to, and some people have been pointing out, I saw Van earlier here, but there are some things going on if you do big buffers that we haven't run into yet and may not even run into. And the users want the network to work 365 days a year, and I was having a laugh. I saw some ad from some beer company that said it was 364 days of practice, and then there was St. Patrick's Day, and this year it is actually 366 days. So. This is a simple view of the internet. We have the user at the end, at the very far end there. There are two things that looks like Ethernet at the end of the routers, and usually they are Ethernets. Okay, that's the most common way of connecting computers today. I think everything else is legacy stuff. Ethernet runs at all sorts of speeds. Then there's a router, there's a tail circuit, and it goes into the middle of the network. And in the middle of the network, you want to be able to carry larger packets than 1,500 if you want to encapsulate or whatever you want to do with them. There's also a game called bandwidth delay quota, which is basically how much buffering you can deal with in any point of the network where you can get congestion. And for many years now, we've been playing around and say the maximum delay of the network is 350 milliseconds. And if your Ethernets are 100 megabits, that you can't put any bigger stream onto the network. So 100 megabits times 350 milliseconds is 4.4 megabytes. And it turns out from empirical experiments that if you have 3 times that in your router, you're always fine. The core of the network looks usually sometimes like this. And some people use the switches here, and some people use the router. And it doesn't really, as long as the elements put in there adhere to the requirements we laid out earlier, it doesn't really matter. But it looks like kind of this, that you have some kind of high-performance devices in the middle, and you have wide area circuits. And a network can look like this. This is in no way, shape, or form a typical backbone, but if you can imagine this being the U.S. and a subsection of the U.S., the East Coast and West Coast, and kind of a little bit similarity about reality. But this is what most people are doing today, and today OC48 over optics, over WDM system is like off-the-shelf thing. You can buy it at the Kmart, and I think most people are building networks that way. In my hometown, we are using that for delivering to old middle-aged ladies their basic connectivity, so it's not very complicated. If you go look at the top, we have the access. We have the core routers in the upper right, upper left corner. There are the 3 backbone routers. And this picture doesn't show the wide area circuits. And then some people think that the internet is World Wide Web, so they say you have to have content. And then you have users and customers, and they are usually connected with something. And traditionally, there are T1s, E1, ATM, OC3s, and whatsoever that connects from our access boxes. And there may be a layer of frame relay and ATM switches in there too. And in between the access routers and the core, depending on who you're talking to, they have some kind of oversubscription factor. They say, well, if you buy a T1, you're not going to use all your T1, you're only going to use 30% or 10% or so. It depends on who you talk to. Now, how do we interconnect the stuff in the middle here where I left spaces open? Well, if you look at the web form for a second, you can put some kind of switch there. And that means that this switch is going to be the thing where you come from a slow pipe to a big pipe. And if you want to sell subrates to this Ethernet-based workstations or servers that sits on that, it looks like PCs, this smart switch there has to do all your policy. So the point of policy is done there. So my way of viewing it, this is usually called the layer 1, 2, 3, 4, 5, 6 something switch. But in reality, it's just a big router that can do policy and queuing, right? So if you connect a server farm, the thing you put between your routers and the servers has to implement the policy on when to back off, how to do bandwidth limitations, and this is where the buffers get built up because that's the point of congestion. With policy here, I mean anything like congestion, that you rate limit them, that you do access list or something. So we end up finding that we have to have an element there that looks like a router, and you may ask yourself the question, why did I put another box there that actually does the same thing as the big backbone box? It's just that I got some kind of logical separation. Now I'll go to the part of the network that I do understand a little bit more about. If you want to go from your core to your access boxes, and you take 100 megabit Ethernets, and 100 megabit Ethernet 101, you go buy a hub. It's $26 or something, and you connect the cables like this. This has an interesting property. It's half duplex, right? But when the thing in the middle, the Ethernet hub, gets congested, and there are 3 points of where you can get congestion and policy. It's on the core router, on the access router, facing the Ethernet switch, and then downwards towards the customer, because it's a customer. If we get too much packets from the network going towards the customer, you got T3 worth of packets going down to T1, we have to do something. And the simplest thing is just first try to buffer, and if the buffer isn't big enough, drop it. Or we may have different queuing algorithms or dropping algorithms, so we would have access lists that put different kind of packets into different queues. But it's a place where you apply policy. The interesting thing with a setup like this is that when you get congestion in the Ethernet segment, you get pushback into all the routers. So if the backbone router, the middle backbone router, is trying to send to the middle access router, and there's already 100 megabit worth of traffic on the Ethernet, it can't get on the Ethernet because it will get collisions, or first it will wait until the Ethernet is freed up, and then it will start to transmit, and you get congestions. So the queue gets built up in the router. So whatever smart router you have, you only need to tell the router what to do when you get congestion in there. There's no more magic, right? So it's either stored in the backbone router or the access router, nowhere else. So there's nothing, no more other place where you have to apply policy. This limits the packet size that I can send to the same packet size that I can get from the user. So this is not very funny. If you take your customer data and you're trying to do a VPN by putting them 1,500 byte packets slap an IP header on there, it won't fit. So you have to fragment, and then your performance is out of toilet. Some people do this. They go buy a dumb ether switch. A dumb ether switch is a switch that just switches packets, and it doesn't do anything more intelligent than just switching packets. If you put big enough gigabit or 10 gig Ethernets on the top and slow enough Ethernets on the bottom, and make sure that you never oversubscribe the circuits that goes to your backbone boxes, you actually get rid of 1 point policy, because now there is always going to be capacity there. Okay? But you still have going out of the switch, because you can come off the backbone router at 1 gig, build up a queue towards one of the access routers that may be running at 100 meg. So if that queue gets built up too high, the dumb switch will just drop packets. Okay? And most switches that you buy for 168 bucks at Fry's don't do very intelligent things. And the first picture has no redundancy. If something breaks, you're toast. So if you want to do redundancy, you have to take 2 of those boxes, and now you consume twice as many interfaces, and then you have to use a routing protocol to figure out which one to use. And if you use an IGP, the IGP is not going to detect that you lost the path for a box very fast. You're talking about minutes here, so it's not very funny. You can go get a smart ether switch to get rid of the queuing problem at least, but a smart ether switch is just a router, right? It has to do the same thing. So now you end up having to configure your backbone boxes to do the right thing. You have to figure out how the backbone boxes and the access boxes interact with the switch, and configure the switch, which probably speaks another language, to do the right thing, which is all doable, but you end up having more elements. And the only thing you really did was to replace ports on your backbone box with ports on the Ethernet switch. And yes, the way the vendors charge for ports on the routers, this makes economical sense, but it didn't really make my network much better. At a small ISP, where I was spending a lot of time, we used to have a network that looked like this. We had backbone routers, and we had point-to-point packet over SONET circuits. They don't have the property that they can actually support large packets, but yes, they were slow, and they were pretty hard to traffic manage. It's kind of really, it's not very flexible to build something like this where you have a lot of point-to-point links, because if you want to shift some bandwidth over to another access box, it's not very doable. But this solved some of the problems, and the policy was kept inside the routers, because the only other element in there is a piece of fiber between the boxes. Let's see here. Okay. I'm keeping you guys from beer, so I know I understand I have to hurry up. Now, I went and talked to our router vendor and said, hey, do something. And I think the previous speaker probably said everything about SRP before I entered the room. But the key thing here are two. First of all, it's the spatial reuse thing, right? What I'm using between two of the boxes next to each other, that bandwidth is not allocated elsewhere on the ring. So on an Ethernet hub, right, which is not a switch, two guys talk, the entire hub is blocked. Here, if two nodes next to each other are talking, only that piece of fiber is occupied by the traffic, it can be reused again. The other interesting property of this thing is that once you put the packet on the wire, you have an output queue from the router that goes to the fiber. Once it gets on the fiber, it's actually going to stay there. So that means that once you got the seat on the flight, even if the flight stops in 15 cities before you get to your destination, they're not going to take you off. They're not going to take you off the plane and reapply the queuing algorithm. Which means that if the router does a policy decision, it's actually going to be the policy decision that we stick with, because if the router makes a decision to use its scarce resource of the bandwidth towards the ring to send somebody a packet, the packet will get to the destination. It's not going to get bumped up by somebody else. We moved from the point-to-point links to something that looks like this, where we slice the ring. So we put this SRP ring between multiple backbone boxes and multiple access boxes to make use of this spatial reuse thing. And in a scenario like this, you lose a box. You will lose bandwidth on the ring. Either more boxes get served by the same backbone box because it goes into bypass, or the ring get wrapped. But this is an ideal scenario, because if you wrap the ring, you don't really lose any bandwidth because it's only two nodes on there. Everybody talks about quality of service, and an SRP ring only has two priority queues, high and low, and high is really like a dangerous tool because it doesn't apply to the fairness algorithm. So once you put things in the high queue, you really don't have any control. So you have to think manually to do that. Once you put things in a low priority queue, you can play with it. And in order to make efficient use of a media like this, what you have to do is you have to have virtual output queues on your router feeding the ring, where you can put your packets into different classes, and then you schedule them out to the shared resource. And this actually works, and it's pretty kind of okay, and it doesn't have any of the problems, and it doesn't introduce another element that we have to talk to. Somebody tried to tell me, well, we can build a ring out of switches. So if you take Ethernet switches and you put point-to-point gig ethers or 10 gig ethers, and you do something like this, you run spanning tree, and spanning tree defines one box as a root, and then it wants to see a tree, not a ring. So what's going to happen if you turn on spanning tree on a topology like this, it's not going to use the segment in the bottom, because the tree of the root is on top. So you really only use half of your ring. Yes, you have redundancy. With old spanning tree, it took basically a minute or so to recover. They have done lots of changes today in like 4 or 5 RTTs can actually reconfigure the spanning tree. So they've done a lot of work there on the switch side, but you still can't get access to that. And the second thing is this: when once packet comes on the wire going downstream and new packets come into the same box, there is no precedence. I haven't seen any. Of course, you can do this, maybe, but I haven't seen anybody doing it. There's no way where those boxes can deal with the fact that some traffic is already policed that has to go, versus some traffic just goes entered to the box locally. So putting switches in a ring doesn't really do the same thing as doing a ring of routers. And even if you put routers behind the switches, you now have the worst of everything. So this is where we kind of are today, and then we go scratch our head and say, I scratch my head and said, how do I make the network bigger? Because we have this nasty thing called customers that we have to deal with. If we didn't have customers, life would be good. Now, if you take one of the biggest boxes, and I think this actually applies to all the big boxes you can buy, they seem to have 16 times OC192. Some of them uses 2 slots for the brain substitute, the thinking device, and you may use 1 or 2 of them. If you play around with this device and say, okay, what's the biggest network I can build with this that actually works? I, in this example, have used 6 slots out of my 16. I used up 2 or 1 for the RP. I used up 6 for access. And then you need to interconnect your boxes, and then I have 5 or 4 depending on how many brains you have. left over on each box to connect your wide area links. So if you do something like this, you take all your access boxes and you put them in a ring, and you break the ring the same way we did on the first page, but assume that in this picture the blue, green, and red SRP rings or DPT rings or whatever the marketeers choose to call it this week are running at OC48 speed. You have 2 times OC48 on each of those rings. If each of the small boxes have 2 times OC48 worth of customers coming in, I got an oversubscription of 4 to 1 on the ring. It's an interesting scenario because it's 4 to 1 on the ring, but it's actually bottlenecked before it gets to the router. So if I have transit traffic on my IP network, I actually have more capacity in the transit network than I have on the access side. I know that doesn't make sense, but let me show some more pictures. Now is where I wanted to put the picture of the grave of the engineers. I said something stupid again? I had 2 girls back here. Okay. Are any of them blonde? So this is where I wanted to put the picture of the grave of the engineers because I ended up finding that this looked like some religious symbol. This is the biggest you can build with a 16-port router using, basically you have 2 switches in here. One switch is the fabric of your router. The other switch is your access ring. And the access ring is actually one single ring that goes around that is broken up in 9 segments. Okay? And they're not shown on this picture are the 4 slots left that goes to every pop of the wide area circuits. Okay? You can't double this again because then you will use all your ports to interconnect boxes in your pop, and you don't get any slots to connect your wide area circuits. So with this I get 9 routers, 108 access routers. I get 36 OC192s worth of wide area capacity, or if you count in OC48, is 144 OC48s. Or if you pull one of the RPs out and only have one, you get 45 OC192s and 180 OC48s worth of capacity. Now, if you count DS3s, you get 6,000, basically 7,000 or 8,600 DS3s worth of trunk capacity. If we did 4 to 1 oversubscription between the access boxes shown in the picture and the core boxes, I can support 10,000 DS3s with this pop. So I have 10,000 DS3s coming out of that box. But with the 4 to 1 oversubscription, that's less bandwidth than I have for trunk. Right? The funny thing with this is completely redundant for everything. Yes, you may lose capacity if you lose a box, but you're never going to lose connectivity. And losing a box is not too bad with the kind of traffic patterns we have. So this is fully redundant up to the access box, and there is no protection switching for DS3s anyway. So you just you have to dual home your customers. So if you take the old backbone, I love projectors. If you take the old backbone, right, then the reason for adding more circuits is that we have more customers, we have more traffic. And for every point-to-point link, like with pop A to pop B, there are 8 circuits, okay? I assume that the 4 top of them are 4 OC192s that are 4 wavelengths on the same fiber. And then there are the dashed ones, there are 4 dashed ones below them, they have to go on another fiber path. And the real requirements between those pops are probably in the 4 or 6, the optical OC192s, because if you cut the fiber, you will lose capacity. Now, everybody talks about 60 milliseconds and restorations and protection, and I was going to mention the N word today. If you look at a network like this, it's a spaghetti. And I think the professionals call this mesh network. So when you look at this from a survivability point, okay, the things that's going to break, the significant thing you can lose here are EDFA, optical amplifiers, and fibers. Okay, losing a router doesn't show up. I mean, if you put optical switches between the POP and the long haul fiber, you can do what people call traffic engineering. So I have a suggestion for local area traffic engineering tools. If you take a wire-guided missile and you put it on your roof, on your POP, with some kind of stuff you have for satellite antennas, so you can actually aim, and you replace the copper wire they're using for guiding the missile with fiber. The only thing you need to your MPLS, LSP, RSVP configuration system is to tell customer building location, height of building, and type of roof. And it will launch the missile with the fiber, bandwidth on demand. Now, I'm showing, so my point is that when I did this, I had 1+1, right? I put twice as much capacity in as I really need. This is a safe way of living. In reality, you want to sell the shit out of this. So you may sit down and scratch your head and figure out where would I actually have capacity that can be used for restoration. And it turns out every time I try that, it doesn't work. It always ends up being something you didn't think of, and it's even worse if you do trafficking in your path. Yes, it's nice, but you can't figure out all the states this thing may end up in. So throwing fiber at the problem is really nice, and it keeps the customers very happy, and they say, "Mom, send money." Anyway, in a network like this, the thing that actually is going to break is BGP, because ISIS, which is IGP, is actually fine even for this spaghetti. But using the BGP, the external routing protocol, as an IGP, as we're doing, makes it really hard, because we have 120 nodes in each POP, served by the router sector. And yes, it works, but the propagation times are awful. You want to restore around the problem in less than a second, and you just can't send updates fast enough using TCP with existing stuff. And it's actually where we have to do some new work. So, observation from this little exercise is that if you look at this, you say, "Oh, it's a lot of boxes." I go look at the real network. We have lots of boxes. They're just really dumb and stupid small boxes. So the number of boxes doesn't really change. It can keep a large ISP. Okay, so the largest ISP is 3 times my example, right? So, and they double every 9 months. So somebody producing big boxes has to deliver the big box before March 2002, because I can't figure out a way to make a network bigger with existing stuff. Another observation that I found was 10,000 DS3s going out of the building to customers. DS3s is PDH stuff, right? And then if you add up how much money the SONET and that stuff costs, it's more money than I spend on the routers. And it has to be optical, because DS3 runs 30 feet or 10 meters or something over coax. So maybe they have to put fiber into the building. And if they put fiber into the building, maybe I should take my access ring and run it all the way to the building instead, and not buying the SONET ADM, not buying the DAX, not buying the SONET ADM, and not buying the line card. So I think that sometime during this evaluation curve, we are going to change things, because we get to the point where we have to put fibers into the building, and maybe I just put a router there. Either I run the DS3 back-to-back in the building, or I hand them off an Ethernet plug and say, "Here is your DMARC." Or I'd go find something that speaks Ethernet over optics, but then go back to switches in the middle that doesn't understand what I understand, that doesn't do what I want. That's it. As usual, this is not what do you do? How do you, this is a big disclaimer, okay? This is the thinking we have around what we can and can't do, how we can design a network, what we're looking at doing, what we can and can't do. This is not what we're doing. It's not a commitment from anybody, including the people on the bottom there. But we promise to have the best network around. Questions? Thank you. Beer.